Have you ever just looked up at the sky, seen a massive jumbo jet soaring overhead, and thought, how? I mean, seriously, how does something that heavy, that huge, get off the ground and just stay there? Well, we're going to dive right into that because the answer is this absolutely beautiful dance of physics, and it all happens in an invisible world that's all around us.
I mean, it's a great question, right? We're talking about a machine that can weigh 400 tons. That's like 100 elephants, just casually hanging out 30,000 feet up in the sky. It feels like it should be impossible. But spoiler alert, it's not magic, it's science. And to really get it, we first have to understand the stuff the airplane is flying through, the air itself.
You know, we tend to think of the air as just empty space. But that's the first big idea we need to throw out. The atmosphere isn't a void, it's a substance. A much better way to picture it is to think of it as an invisible ocean, and we're all living right at the bottom of it. And this ocean, it's got stuff in it. It's a real physical mix of gases, mostly nitrogen and oxygen, and all of that has mass and weight. So every single second, the entire weight of this massive ocean of air is pressing down on everything, including you and me. That's the crucial thing to remember. Air is a physical thing.
So because air is a physical thing, it has properties we can actually measure and study. And it turns out there are 3 key properties that are absolutely essential for making flight possible. So let's break them down, one by one.
First up, air is a fluid. Now, when we hear the word fluid, we usually think of water or other liquids, right? But gases count too. All it means is that air doesn't have a fixed shape, and this is the important part, it can flow. This ability to flow is like step 1 for everything else in aerodynamics. Second, every fluid has something called viscosity. It's kind of a fancy word, but all it really means is its resistance to flowing. You can just think of it as thickness. And the great news for airplanes is that air has an extremely low viscosity. It's thin, which means it moves out of the way with almost no effort at all. And this makes total sense when you think about it. You know, honey, grease, they're thick. They really resist flowing. But air, it's way over on the other side of the scale, in the thin category, with stuff like water or gasoline. It barely puts up a fight, which is exactly what you want if you're trying to blast through it at 500 miles per hour. And third, because our big ocean of air has weight, it's always pushing down, exerting a force on everything inside of it. We call that force pressure. And pressure is the key that's going to unlock this whole mystery of lift.
Just to put a number on it for you, at sea level, that invisible ocean is pressing on every single square inch of your body with about 14.7 pounds of force. That's a huge amount of pressure. And it's this very pressure that an airplane wing is so brilliantly designed to manipulate.
Okay, so we've got a fluid that flows super easily and is always exerting pressure. How in the world does a simple wing use that to create lift? Well, it all comes down to 2 brilliant principles of physics working together in perfect harmony.
The first piece of the puzzle is something called Bernoulli's principle. It's a fundamental rule for fluids, and it basically says this: when a fluid speeds up, its internal pressure goes down. And the classic way to see this in action is with a device called a venturi tube. Okay, so check this out. Air flows into the tube at a normal speed and pressure. But to get through that skinny middle section, it has to squeeze through a smaller space, which forces it to speed up. And just like Bernoulli said, right there where the speed is highest, the pressure is lowest. Then, as it comes out the other side, it slows back down and the pressure goes back up. And here it is. This is the big aha moment. An airplane wing, what they call an airfoil, is basically just half of a venturi tube turned on its side. That curved top surface forces the air flowing over it to travel a longer path, and because of that, it has to speed up, just like in the tube. Faster air on top means lower pressure on top. It's that simple.
But hold on, that's only one half of the story. The other half comes from a guy you've probably heard of, Sir Isaac Newton. And you definitely know this one. For every action, there is an equal and opposite reaction.
So here's the other piece. A wing is also angled so that it physically shoves air downwards as it cuts through the sky. That downward push on the air, that's the action. And Newton tells us the air has to push back with an equal and opposite force. That reaction is an upward push on the wing. So you see, both principles are happening at the same time. The pressure difference and the action-reaction combo. They create that incredible upward force we call lift.
Okay, so all of this works perfectly.
in a textbook. But pilots aren't flying in a textbook, are they? They're flying in the real atmosphere, which is messy and always changing. And those changes have very, very real consequences on how a plane performs.
One of the biggest challenges is what pilots call thin air, or high-density altitude. When the air is less dense, it hits the aircraft with a triple whammy. 1, the engine gets less air, so it makes less power. 2, the propeller has less air to bite into, so it creates less thrust. And 3, crucially, the wing has less air to push down on, so it generates less lift. It's bad news all around.
And what causes this thin air? Well, it's a combination of 3 things, being at a high elevation, hot temperatures, and high humidity. That's why a hot, humid day at a high-altitude airport like Denver can be an absolute nightmare for a pilot. The plane performs as if it's way higher than it actually is, meaning it needs a lot more runway to take off, and it's going to climb a lot slower.
There's another really fascinating real-world problem. Remember, we've got high pressure under the wing and low pressure on top. Well, nature hates that imbalance. So the high-pressure air is always trying to leak around the edge of the wing to get to the low-pressure area on top. It does this by creating a powerful swirling vortex of air that spins off the wingtip, which wastes energy and reduces lift.
And the solution that engineers came up with is just so cool and elegant. You've definitely seen these on modern jets. The tips of the wings are bent upwards. Those are called winglets, and they basically act like a tiny dam. They physically block that air from spilling over the top, which messes up the vortex, cuts down on drag, and makes the whole wing way more efficient. Just a simple, brilliant fix for a complex problem.
So, the next time you're at an airport, or you just happen to see a contrail streaking across the blue sky, I hope you see it a little bit differently, because it's not just a machine. It really is a masterclass in physics, effortlessly manipulating an invisible ocean using principles figured out centuries ago to conquer gravity, one flight at a time.